So in this next lecture, we will show how one could sketch three-dimensional surfaces on a two-dimensional page or system. It generally is difficult to do, however, if you keep certain things in mind, essentially projections, we might be able to show what these three-dimensional objects look like on this two-dimensional page. So there are some guidelines which I will generally present by way of example. Essentially what one needs to keep in mind is we're going to project the equation onto the various planes. So first of all, if you look at a three-dimensional system, we have the x-axis, y-axis and z-axis. So that is the xz plane, the floor is the xy plane, and what's against the page or the page itself is the zy plane. So the plane that is coming out of the page is the xz plane. So by way of example, and we look at a number of these, some standard examples, we will now consider the surface z equal to x squared plus y squared, say. So to project, say, onto the zx plane, we will let y equal to 0 or y equal to constant. So it's clear that when y is equal to 0, we get the parabola z equals x squared. So this is in the zx system. What we get is, if that is the x-axis and this is the z-axis, we have a parabola of that type. Secondly, if we do a similar thing in the zy plane, we could let x equal to a constant or x equal to 0. If x equals 0, we're projecting directly onto the zy plane. So that is the zy plane. That's the z-axis. The vertical axis is z. The horizontal axis is y. We get again a parabola. So keep in mind this: in the zx case, the parabola is coming out of the page. In the zy case, the parabola is on the page. Now what happens when we project onto the floor, the xy plane? Well, instead of saying let z equal 0, we'll say let z equal to a constant. So when we consider the xy coordinates, right, we will say z equals some constant. In that case, what we get is that x squared plus y squared equals this arbitrary constant, say k. And we know that this in the xy system is a circle. So there's your xy system, and what we get are circles. And what we need to do is to put these three things together on the resultant three-dimensional system. So therefore then, the three-dimensional system we're going to look at, well, this is what we have. We have the x, y, and z system of axes. So coming out of the page, I'll indicate that in different color. In the xz plane, we have this parabola. The dotted lines go into the page. On the page itself, we have again a parabola, but this one is on the page itself. That is the zy plane. So we have this is on the page. And in the xy coordinates, i.e. when we're looking down the zy axis, we're seeing circles. In other words, the cross sections are all circles with equation x squared plus y squared equal to a constant. So what we have there are these things. These cross sections are all circles. And this is what we call the paraboloid with cross section circles, or circular paraboloid. So this is then referred to as the circular paraboloid. Circular paraboloid. paraboloid. If in the case of C, that is the projection in the xy case, if your equation was x squared plus some other constant y squared, like x squared plus 3y squared equal constant, the cross section would be ellipses, in which case this would be a elliptical paraboloid. Now in example 2, we'll move on. We'll consider a rather simple equation. This is the equation 2x squared plus y squared plus z squared equals 2, say. The 2 is just a constant that is positive. It's clear that if you put z equal to 0, let's start with z equal to 0, that is the projection in the xy case, right? We'll end up with an equation that looks like 2x squared plus y squared equals a constant. So you've got 2 plus z squared, 2 plus a constant. So this is something like that. And you know this is an ellipse. So in the xy coordinates, this is an ellipse. Xy coordinates. If you look at the xz coordinates, this is now the projection onto the page or the wall that's coming out of the page. We get 2x squared plus z squared equals 2 minus y squared, which will be another constant. We're ignoring the y coordinate. So this would be, say, k1. So in this case too, we have an ellipse. So in the xz coordinates, we have again an elliptic shape. And lastly, in the yz coordinates, that is when we put x equal to a constant, we get y squared plus z squared equals to 2 minus some constant. Let's say it's positive constant. That will be, say, k2. Since the coefficients of y squared and z squared are both 1, this gives us a circle in these coordinates. So in the yz coordinates, we've got a circle like so. And if you put that information together on a three-dimensional system, so the three-dimensional system would look like so. This is the x, y, z system. In the yz system we have circles, but every other system we have ellipses. So if you look on the wall, let's start off with the wall that's coming out of the page. You've got an ellipse, and if you look at the xy system, that is the system that's on the floor. You also have ellipses. This is on the floor. And in the zy coordinates, you've got circles coming. So this is the projection onto the zy plane. So let's try to choose a different color. You've got these circles. So in the end, you've got this elliptic structure that looks approximately like so. If you put all the ellipses together and they have cross sections, these circles. Looks a bit like a rugby ball if you want. Then going on to, we'll go through a number of examples, and these examples will indicate a general procedure for constructing these three-dimensional surfaces. So here we get into a class of standard surfaces. Let's look at this. Look at the next 2-3 examples in the same sense. If we have 2x squared plus y squared, say, minus z squared equals, and there the emphasis is we have a positive 2, any positive constant. Right, so one needs to know what these shapes would look like when you let one of them equal to a 0 or a constant. So again, if you look at the xy coordinates, right, in that case you have z is a constant, so you have the approximate equation 2x squared plus y squared equals some constant, right? So that in the xy coordinate would be ellipses. So without sketching, so these are elliptic. That's in the xy coordinates. in the xz coordinates, you have something that looks like 2x squared minus z squared equals a constant, because you're letting now your y equal to a constant, so you got something like 2 plus something, so let's leave it like that. Those, you know, are from first year hyperbole, but they're specifically hyperbole that cross the z-axis. So if this is your x-axis and this is your z-axis, these would be hyperbole that crosses the so these would be, if you put, for example, z equal to a 0, you get 2x squared equal to constant. So I'm trying to remember what this would look like if you were to sketch this. So that would look like that, hyperbole. And you get a similar thing in the let's go back, this is the remaining case is the yz case. The yz case, very similarly, you're putting y equal to a constant, you get 2x squared minus z squared equal to some constant. You also, these are hyperbole, and you get hyperbole again. Let's write that nicely. These would be hyperbole. And these two would be hyperbole. So you've got these hyperbole in the xz coordinates and in the yz coordinates, and when you rotate them, when you project onto the xy axis, you get ellipses. So the cross sections are ellipses. So in two cases you get hyperbole. Maybe I should draw the one more case here. This is the case when you've got the y coordinate with the z coordinate. So here too you get hyperbole that look like that. So look at this, in the xz and yz coordinates you got this hyperbole, and when you're looking down the z-axis, that is when you're projecting in the xy case, you got these ellipses, these ellipses here. Okay, now you need to try to imagine putting this together. So if you put that together, we've got, well, what are the axes looking like? You've got the x-axis, you've got the y-axis, and you've got the z-axis. So you've got these hyperbole doing like that in the zy case. You've got the hyperbole doing that in coming out of the page, and this is inside the page. Look at that. Okay. So imagine these hyperbole are then having cross-section circles. So when you're projecting in the xy case, you got these, not circles, ellipses. Okay. And if you put all that together, what if you can imagine that this is what you finally get. Okay. So you've got these, what's called a hyperbola of one sheet. It's a single sheet. So these are hyperbole of one sheet. One sheet. Okay, so that's example 3. I'd like to call this next example, example 3 star instead of 4. Because it's somehow related to or similar to the example we just had. So in this case, I'm looking at the case 2x squared, very similar to the left-hand side above, plus y squared minus z squared, this time equal to minus 2. Okay. So if you let z equal to 0 or some constant that is large enough, we need to be careful here. So what we need to do now is, let's look at the projection in the xy case. And if we let z equal to a constant, let's not let it equal to 0, because there's something funny going on here. This is equal to minus 2 plus z squared, right? And this z, of course, we're letting equal to a constant. So this we would say is minus 2 plus some constant. Let's call it k squared or something like that. Now on the left hand side, you've got 2x squared plus y squared, which has to be always positive. So this is positive, which means that the right hand side has to be positive also. For the right hand side to be positive, this constant here has to satisfy certain properties. So you have to have k squared minus 2 must be positive or 0. That means k squared must be greater than or equal to 2. And if you solve this, keeping in mind the negative side, that k must be greater than square root 2 or k must be less than minus square root 2. Which means that the z cannot take on values between these two values. So let's just look at what happens now. This is now the projection on the xy system. So, and when this condition is satisfied, the 2x squared plus y squared equal to the constant on the right hand side gives us ellipses. So these are ellipses. Bear in mind that z cannot be between minus root 2 and root 2. Okay, so now let's look at what happens in the other coordinates. Now we're looking at the xz coordinates and the x and the yz coordinates. In the xz coordinates, that means we are now letting y equal to a constant. We get exactly what we get before, which is then 2x squared minus z squared equals some constant, right? And in the other case, we get y squared minus z squared equals some constant, right? In both these cases, we get hyperbole in the respective coordinates. So that in the xz system, if that is your x and this is your z, you get these hyperbole that do that. Okay? And here, if this is your y coordinate and that is your z coordinate, you again get hyperbole. But when you put this system together, you need to be a bit careful, because there are certain z values that are not allowed. And you've got to look at what happens here in the context of what we just developed above. So what we got here is the following. If this is your x and y coordinates or system of axes, and if this is your z axis, so z or k cannot be between minus root 2 and plus root 2. So somewhere there is a root 2, and somewhere inside the ground is a minus root 2. Okay? And these are values of z, or what we call k early on, that are not allowed. In other words, it produces a contradiction. Above this, if you look at the zx coordinate, let's concentrate on the positive side. So this is the part that is coming out of the page. You've got this hyperbole. This is the hyperbole that's going into the page there and there. This is going into the page, hence the dotted line, approximate dot. Then on the page itself, you can say on the wall, we also have hyperbole. So these are so hyperbole also. Okay, but this is on the page, not coming out of the page. Right? And the cross sections, that is when you are looking at planes parallel to the xy axis, you get these ellipses. Okay, let's just go back and see what I mean. And this is what we're looking at. We get these ellipses. Okay, so going back up here in our completion, what we get is these are then ellipses. So you've got these two cups, one facing up and one facing down. The cross section of these cups are ellipses. The surface of these cups are hyperbolic. So there's a hyperbolic shape facing upwards, and that's the one facing upwards, and there's a hyperbolic shape facing downwards, whose cross sections are ellipses, not circles. And this is also a hyperbole, but we call this a hyperboloid of two sheets. So if you want, this is a hyperboloid. I'm not going to spell that out. Hyperboloid of 2 sheets. The previous one was a hyperboloid of 1 sheet. There's one more interesting case that I would have loved to have looked at, but I think we'll have a look at that in some... Well, let's try it. Let's see if we can do a similar thing in the next example. This is example 4. In example 4, let's look at a general equation where we have x squared minus, say, y squared minus z squared equal to some constant. This time I'm going to call the constant k. So we'll do this one quickly. You can see that in the xy system, we have x squared minus y squared equal to k. So you've got we've got another hyperbole, this one crossing the y-axis. So if this is your x equation, axis, and that's a y-axis, you may have these hyperbole. If you look at the xz system, you get something similar, almost the same in fact. You get that's the x and that's a z, you get hyperboloid, right? And then of course, if you're going to look at the next case, you're going to get the yz system. You're going to get x squared minus k. First of all, before we do anything, y squared plus z squared. You notice we get something similar to the previous case. I should perhaps not have gone into this example. You got the right hand side will tell you it's a circle of some type. So you got in the z, y coordinates, you're going to get a circle. So if you let x equal some constant, but again, this left hand side in this case has to be positive. Why? Because on the right hand side you have y squared plus z squared, which is positive. So as long as x is between is greater than the square root of k and less than the minus square root of k, this will be a circle. So you get something exactly as before. You get a hyperboloid of 2 sheets. Okay. I'm going to look at one more general case. And this is an important case because remember we're doing our sketches in a 3-dimensional system. Now this is important. If in the equation, the Cartesian equation, if one of the variables is absent, what you do is you sketch your curve in the given 2 coordinates and then expand or extend that shape into the remaining variable. This is what I mean. Let's do this by way of examples. These are now sub-examples. If you have, for example, y equals z, z equals, let's make this interesting. Let's make this z equals y squared. Now remember, we know this is a very simple parabola in the yz coordinates. That's your z-axis, so we get as a parabola. But that's a 2-dimensional system. If we expected to sketch the surface z equal to y squared, i.e. in 3 dimensions, we sketch the parabola z equal to y squared on the zy plane and project and extend this into the remaining x-axis system. This is what I mean. Now going on to the 3-dimensional system for the same equation. This is the x-axis which is not featured in the equation. This is y and that is z. So we said that in the zy system, this is what we have. So this is on the page zy. The absence of the x means that you have the same parabola z equal to y squared for any arbitrary value of x on the positive side and on the negative side. So if x is equal to 100, we have the same parabola. If x is equal to minus 100, which is in the page, we have another parabola. So what we've done is we're taking this main parabola on the zy plane and we're extending it like so in the remaining variable, which is x. So what we end up with, if you want to shade it up, is this surface here is parabolic, and this is inside. So you've got something that looks like a gutter that is of parabolic shape. You've got something that does this. Okay. And these are all parabolic. And that's why we even get the equation of the circular cylinder coming up in the following case. And incidentally, this is called, all these in which one of the variables is missing are called cylinders. So this is a parabolic cylinder. In this next sub-example, right, we'll look at, say, x squared plus y squared equals 4. This we know is a circle in the xy coordinates, like so. So when we sketch this in 3 dimensions, to do this very quickly, there's the x-axis, there's the y-axis. Remember, the xy plane, the xy system is on the floor. So this is the circle we have on the floor. That's a circle. That's on the floor. The z is missing. That means this circle is valid for any value of z. So you take the circle and you project it in the z direction. Up like so, and down like so. And all these cross sections are circular. Okay. And this is called the circular cylinder. So your standard cylinder is in fact your circular cylinder. Circular cylinder. So the previous one was a parabolic cylinder. The parabolic cylinder is generated in the x direction. This circular cylinder is generated in the z direction. I have one more example to do, and that's called the saddle, but I'll look at that next time. So have a look at this. Try to get a hang of how one can represent 3-dimensional surfaces on a 2-dimensional page.